Hello everyone, my name is Raoyuan Zhao, and I'm a second-year PhD student at the MaiNLP lab, which is also part of CIS and at the University of Munich. I'm also a junior member with MCML. Today, I'm very glad here to give you a talk which titled Synthetic Data for LLM Variation toward Dynamic, Scalable, and Multilingual Assessment. And I also want to thank you for Florent and Galina's amazing talk. They mainly focus on the synthetic data generation, but for my talk, I mainly focus on how could we utilize the synthetic data. I have two main focus. One is evaluation, the other is for training. Here is the menu of today. First, I will give you a brief introduction about the background of the LLM's evaluation. Then I will raise some research questions. Then I will show my two finished projects with you, which one is smart typo, the other is called reverse math. Then I will also give you a brief introduction of my other finished projects, then come to a conclusion. So let's start. Let's think about why evaluation matters to the LLMs. I believe all of you have suffered a lot of exams to be here today. And we all know exams are very essential. It not only tells us what we have already learned, but it also helps us to detect our weakness, what we should still work on. So exams to all human beings is just like evaluation to LLMs. And think about the exams we take in the past. When we are in the elementary school, the mathematical exam is very simple. It's just 1 + 1 = what? But when we go to the college, mathematics changes. It begins to ask you calculus, linear algebra, which is much more difficult. It's same for the LLM. LLM evolves every day and it becomes more and more capable and more sophisticated. But current evaluation method, they usually rely on fixed benchmark. It stays in the elementary level sometimes. For instance, currently one of the very popular benchmark for common sense tasks is called MMU. It's proposed years ago, but now it's still widely used for these so strong and advanced LLMs. So here comes to our first research questions. How could we make this evaluation also evolve like LLMs? And also there's a second point. I believe we come from different countries. When we have exams, we do not have original English questions, then we translate it into Chinese, German, or Russian. Instead, we have all original generated native language questions. It's more aligned with our local knowledge or local culture. So here I come to the second research questions. How can we ensure fair multilingual evaluation? Because currently many multilingual evaluation, they just have original English benchmark. Then they utilize the machine translation to translate this question to corresponding languages and assume it's fair. But actually, in real cases, sometimes it can introduce some bias. And also, when we found all this weakness, what is the next? We shouldn't stop here because the aim of the exam is not only to help you to tell you, okay, you are weak, but also it wants to help you to improve. So here I come to the third question. How can evaluation results help to improve the LLMs? Synthetic data could be a good solution to these questions. For instance, for the static and saturated benchmarks, once we have developed a synthetic data framework, we can generate as much data as we want automatically. And also because it's generated by LLMs or by some rule-based algorithm, it do not need any human efforts, which can also avoid the expensive human annotation also. And also, LLM itself has a very strong multilingual generation capabilities. We do not need to first have English, then do machine translation. By avoiding using machine translation, we can also avoid the potential bias could be introduced. And because synthetic data is generated data, it cannot be sure before. So it can also very useful to avoid the data leakage issues. But for synthetic data itself, it also has some challenging points. For instance, how can we ensure synthetic data is reliable? How could we ensure the synthetic data is diverse? And how could we generate this data efficiently? Okay, so then come to my first project I want to share with you. We all know people are lazy, and when we talk with the AI chatbot, we are also do not care too much about our inputs. We can make some mistakes, for instance, typos. And in the real world scenario, users always make some imperfect inputs. How robust are LLMs to this noisy multilingual input? In this project, we focus on to aim to achieve automatic, multilingual, reliable, diversity, and efficient aspects. So we propose a project titled Evaluating Robustness of Large Language Models Against Multilingual Typographical Errors. This paper has just accepted by the ACL 2026. Let's look at these figures. We have three same questions, but in different languages, in German, English, and Russian. We ask the same LLM to answer these questions. As you can see, with this perfect clean input, the model can always answer with a correct answer. However, when we introduce some typos into these questions, the model, all these three questions can fail the model, which means the LLM are not so robust as we imagine to these easy typos. However, existing benchmark, they always assume that the data are perfectly fine, and these benchmark are always use this grammatical perfect data, or they just use a very naive typo algorithm to insert very few and random characters into the questions. So we need a realistic language-specific noise generation algorithm. So we introduced the MaiNLP. This is an algorithm to help to generate multilingual typo data. You can input a clean data, and we will help you to generate data contains some realistic typos. What the realistic typo means, you can see here is the comparison. In the left side is a very commonly used naive algorithm. When we want to type cat, when we want to type the T, the naive algorithm just randomly sample one key from the whole keyboards. But in our algorithm, we will consider about the actual word keys position in the keyboard. When we do the typing, users are only most likely to type the keys surrounding these T keys. And we also can choose the typo ratio to control how frequent the typo appear in the data. Here is how our pipelines look like. First, we have input test. They are perfectly clean. And we do some word sampling to sample one word from the test. We refer to some previous linguistic studies which they have some empirical experience of in which position of the sentence is more likely to have the typo. And the users here can choose the typo rate they want. For instance, here we set the rate to 0.1. Here we have 10 words, so we will only sample one word from the sentences. And after obtaining these words, we will continue doing another sampling, what is position sampling. Because for when you type in a word, the typos happen probabilities of the different position of the word is also different. We also take that into consideration and randomly sample one position of the character, which we will apply some typo operations. For instance, we replace one character of this word, or we swap two characters in this word, or we just randomly delete one. And after obtaining this, we obtain this synthetic typo data. We use this to evaluate LLM with different tasks. Like previously I mentioned, we aim to provide more human-like typos. So we conduct kind of human evaluations to prove whether we do really be more nature like naive algorithm. Well, we conduct a human evaluation task. First, we sample 13 data from a data set and apply our multiple algorithm and a naive algorithm. And we shuffle all these 16 data and show them to the user, ask the user to decide whether this data is look like a human introduced the typo or the machine introduced the typo. And as you can see here, almost all the languages passed the human evaluation. They believe we are more nature and pass a significant test. The only one outlier is the Arabic. And we think the reason why it do not pass the human evaluation is maybe because it has a very different script system compared to all the other languages. It could be a very interesting future work. And here's the results of the evaluation model's performance on our multiple data and the original clean data. The blue bar means we test in the base version, model's base version, and the red one means it's an instructor version model. And as you can see, also, and this different color lines means different typo rate. And as you can see, although the instructor model always outperform the base model in the clean data set and it's very strong. However, the instructor version model, they are still not robust against these typos. And here is the result of the different model family in different tasks. Here is MMU is multilingual common sense dataset, and MGSM is mathematical reasoning dataset. ProRes 20 is translation task, and XNLI is inference task, and Blabus is reading comprehensions. As you can see, most models, they decrease most in the mathematical reasoning tasks, which means typos have different impact among different kinds of tasks. Okay, and we see multi-typos can help us generate the typo synthetic data, and it can help to detect the model's robustness against this noise data. However, they rely on the fixed benchmark. Even if we introduce typos, it still asks about the same question. It still have the same original question, original answer. And we know that model suffers from data contamination. Model can have memorization. Like this data are all publicly available. Model saw this before, and model remember the answer. Even though model do not know how to solve the question, but it knows the answer, so it can have a shortcut. So here comes to the second question. How can we generate new evaluation data from existing benchmark, which could provide a different answer? In this project, we focus on all these 6 research question aspects. We introduce reverse math, answer inversion for scalable and verifiable mathematical problem generation. Mathematical reasoning is a very popular topic in nowadays NLP communities. Here are 3 very popular benchmarks: GSM 8K, Math 500, MA is very difficult mathematical benchmarks. But all these benchmarks have some issues. They are static. They do not evolve, even though the LLM evolves. And they are all publicly available, so they can have contamination issues. And once they contaminate to the model can train on this data, and the model can suffer from memorization. So even though we observe very high score in these 3 benchmarks, does not really mean the model really do have such strong ability to do the reasoning. Previous work has already tried to solve these issues. One category of this work is introduce perturbation to the existing benchmark. Like what I introduced before is multi-typo. They introduce some typo into the question and ask the model the same question. Or they add some distractors. For instance, they randomly insert some nonsense long text to the question, and to see if the model can still successfully answer the question. And also some of them will use LLM to paraphrase the question. But they all have one issue. Although they have these perturbations, still the answer is the same. Or even a lexical form of the question is very similar to previous one. It cannot successfully avoid the 100% guarantee it can avoid the memorization. And the other way to solve this is symbolic rewrite. One of the most famous work is called GSM symbolic. What they did is they asked some human annotators to look at the mathematical questions, and they construct a template based on these questions, where they convert the numbers, the key numbers in the question, to the placeholders, so they can easily replace the previous numbers with any other number they want to use, only if it's in the defined domain. But although this works already changed the answers, but it also have some limitations. Although it changed numbers, still the new questions follow the similar reasoning paths, and because it involves some human annotators, it's very expensive. So what is missing is how could we generate new problems with new answers automatically. So we propose our framework called reverse math. What we did is, first we have an original problem with this question and the original good answer. Then we randomly mask one numerical value in the question. For instance, here we choose to mask the number 3. And the next, we append the original answer 16 as the known fact to the previous question. Ask a model about what should be the answer to this question is 16, what should be the value of the mask? So we make the thinking tree totally different. And because you may notice this kind of automatically generated problem is not so natural, might confuse the model. In order to avoid this risk, we ask LLM to paraphrase these questions to be in a mature and clear way. And you may ask, if you randomly mask one numbers, how can you ensure that numbers is important? For instance, if we randomly mask 1, we can also result in mask if no one's 1. then the model is impossible to answer these questions. The answer is not unique. That's the reason why we need to verify to prove this new generated data is correct and answerable. So we have the verify part. Here we utilize LLM as the verifier. It has main 3 tasks. First one is LLM should trying to solve these questions. And it should also check the answer uniqueness to check if this question has a unique answer or not. And also, it should also check the leakage of the masked value from context. During the initial experiments, I noticed there are some cases that the answer could hide in the context. For instance, the question will ask, there are 3 people named Leon, Matilda, and Mike, and I masked 3. But still, these 3 people's names retrieve the answer of the masked value. This is the cases we want to avoid. We do not want the answer question become extremely naive or easy. Then, based on these 3 tasks, verifier will have 3 possible outputs. The first one is just directly give the answer to the new questions. And we will apply a rule-based check to compare with these predicted answers and the masked value, because with this paraphrase, they should be exactly the same if we do the rewriting correctly. And if the model, the LLM answer is no unique answer or detect leakage, we will just roll back to the first step, trying to mask another number, do the whole pipeline again. And if we see that the answer is exactly the same as the masked value, we will accept this question as our new generated data. This is how the pipelines look like. And you may be wondering, after this reversal rewriting, will the question become more difficult or not? Here is the result of the different models of different benchmarks. The left column of the data is the accuracy of the model's performance of the model in the original data set without any changes. And the right column is the same data, but apply our reverse math pipeline. And the colors, the red color means the performance decrease, and the green one means the performance increase after rewriting. And the degree of the color means the absolute increase or decrease of the accuracy. As you may see, just with a very quick look, there are no uniform patterns. They are very data and model specific, which means at least from an overall performance perspective, our math referrals do not guarantee to change the question become more difficult or easier. And you may also notice for some models and data sets, it has a very similar performance. There's almost no changes of the model's accuracy. However, does that mean that the models for the individual questions, the model perform exactly the same? So we look at the model behavior changes. Here we report the model's behavior transitions. The beige color means the model in the original questions are incorrect, and after our reverse math is still incorrect. And the same for the deep green, which means the model are always correct. And for the pink one means the previously model are correct in the original answer, but after our rewriting, model failed in the same questions. And the light green means model previously are incorrect. After rewriting, it becomes correct. For the light green cases, previously failed problems become solvable. Could be because after our rewriting, the question become easier, so the model can successfully solve this. And for the cases previously correct answered, later failed, this is the most interesting one. There could be 2 possible explanations. One is that our reverse math make the question more difficult. And the second one is, at the beginning, model is doing memorization, and we may do not change the difficulties just because we change the answer, although the lexical may be very similar, but the thinking paths are totally different. Model cannot do that because it do not have generalization ability, and it's a field. So when the model are doing memorization, it's very likely for the model from the same model family to share the same memorization questions because they share the same pre-training data, similar training methods. So here we study the models which are from same families, previously correct answer, the later incorrect answer, the questions overlap rate. And here you can see there are some clusters in the heat map. And we also conduct a significant test to see if for the model who are in the same family or close to the same family, or their overlap rate have significant differences. As you can see, almost all of them pass the significant test. The only one outlier is GSM 8K. Still, the model within the same family has a higher overlap compared to the model who belongs to different families. And the reason why this one do not pass the significant test could be this dataset is the most easiest one in all these datasets. There do not exist many cases that is perfectly true and false one. And when we look at this perfectly correct answer, later false answer the questions, we found a very interesting phenomenon. We call it answer anchoring. As you can see here, the blue color is the original questions, and we mask the 16 and have our math reverse rewritten questions. And here is the model's answer to the rewritten question. As you can see here, model said 100 minus 101 equals -1, and later model said give a very ridiculous steps. 100 minus absolute value of -1 equals 20. And 20 is exactly the same as the original answer, which means model remember the good answer of the previous one is also a kind of evidence of the model is doing memorization. And we also calculate the different data sets, same as original proportions. And here's the year of the data set is being released. As you can see, as the data set become more and more newer, the same as original proportion will decrease. It's also aligned with our memorization assumption, because for this very earlier released data sets, it's more likely to be appear in the model's training data more frequently. And for the Asian coma, this one is a very new data set. It's only released this year. It has very few same as original ratios. So after we detect the model's weakness and we found the model can do memorization, how could we use this data for training to help improve the model's performance? What we did is we have the original data and we apply our framework reverse math to generate new data and mix these two data to train the model. To prove this data augmentation can really help, we also set up a baseline where we just have the same original data, just duplicate it and apply the same training strategy. Here we are using the reinforcement learning DPO algorithm, GRPO algorithm. And here's the results. The first column is the model without any training. And the second column is the baseline where we duplicate the original data. The third column is our method. We take the reverse math generated data as the augmented data to train the model. And 14 out of 24 of them, they reach the highest performance, which means not only the reverse math can not only use for a very helpful evaluation tool to analyze models' behavior or the potential memorization issues. It can be also very useful to act as a data augmentation method to use for training. That is for that. And then I want also to introduce some other previous finished projects, because all my research is focused on these 6 questions and they focus on different aspects and other domains. The first one is called SYNSI for hybrid behavioral testing of NLP models with static data evaluation checklist. In this paper, I mainly focus on the classification tasks. I utilize the prediction divergence of 2 different models, trying to detect the challenging set for the smaller model. And I'm trying to have extract the patterns from this challenging set to obtain a template, which can be used for generate more and more synthetic challenging set for the models. But this one is mainly focused on the classification task and is relatively early, so it's not about, do not involve LLMs. And the second one is titled, Do We Know What LLMs Don't Know? A Study of Consistency in Knowledge Probing. Here in this paper, I study different kinds of knowledge probing methods. Knowledge probing is used to probe the LLM to check whether the model are certain or uncertain about the answer. And there are many different categories of them. They rely on, they have different principles. Some of them based on calibration, some of them based on token probability, some of them based on prompt engineering. And what I found is that with very little perturbation in the input, the probing methods within the same probing methods or of different probing methods, they give a very different answers. And this paper is called Maki-FAO. This is a multilingual automatic Wikidata-based framework for cultural awareness evaluation for LLMs. Here, I utilize the Wikidata as an anchor, trying to compare models' multilingual cultural awareness capabilities. I propose 4 different metrics, which is diversity, granularity, cultural specificity, cultural consensus. Because Wikidata is a multilingual formatted data, JSON data. So with the help of this, I can also avoid using machine translation to avoid some bias. And the paper is titled "A Comprehensive Evaluation of Multilingual Chain of Thought Reasoning Performance, Consistency, and Faithful Across Languages." In this paper, I investigated of the large language model's multilingual reasoning abilities. I compare the performance of the same question in different languages to see if they will have different accuracy. And also I will check the language compliance of the models, because sometimes when you ask in German, the model still written in English. And this is, I also analyze this kind of phenomena. And I also check the consistency of the models when answering different languages. And I also introduce some error injections in the thinking trees and force the model to directly give the answer to check the model's faithfulness to the thinking trees. And this paper, large language reasoning models are not yet multilingual latent reasoners. It's kind of follow-up of previous work. Here, what I did is I trying to truncate the thinking trees of the models. For instance, it has 100 sentences of thinking trees. I cut them, like in the end, I can cut it only with 1 sentence and ask the model to directly give me the answer. And we observe that the model can already give the answer even if we provide very limited thinking trees, which means the model do not totally rely on the thinking trees to provide the final answer. It can do some kind of latent reasoning. And this one is the most recent work. It involves more about training. It's very popular topic on policy self-distillation. Here we have the same models. Previously, distillation usually have a larger model and a smaller model, and we want to distill the knowledge from the larger model to the smaller model. But for the self-distillation, we just use exactly the same model. But for the teacher model, we will not only provide the question, but we will also provide the answer to the question. But for a student model, it only has the questions. Then we ask them to generate the answers. Then ask the training goal of the student model just to align with the token probability distribution with the teacher model. And we utilize this framework to trying to distill the model's high resource language, for instance, English reasoning to low resource languages reasoning. And we prove that with the help of on-policy self-distillation, it can help model to better do reasoning, even in some very low resource language like African languages. And these are all the other works. If you are interested, you can scan my Google Scholar. And if you want to cooperate, or if you are a master student or interested in doing thesis, you can also feel free to contact me. And that is all for today. I introduced my typo, and I show that robustness the model's robustness is not so strong against the typos, and the evaluation should reflect more about a real-world scenario. And also, I introduced the reverse math. Here, we could automatically generate the new data from the existing benchmark and can help retrieval models memorization phenomenon. So basically, I want to show that the synthetic data can make evaluation more dynamic, informative, and actionable. Thank you very much.